It's really my pleasure and honor to be here, and especially to follow in Stan and Esther's footsteps. And in some ways, I hope that my talk on electrochemical capacitors as energy storage devices will help us kind of bridge the scale from talking about bulk electrochemical processes, if you will, to interfacial processes. So there are three key points that I hope to touch upon in my talk that I was asked to give today. The first is the concept of energy storage at electrochemical interfaces. When we use electrosorption or chemisorption of ions at surfaces, we get excellent electrochemical reversibility. So if you're talking about truly obtaining very, very high powers, tens of kilowatts per kilogram, this is the way to do it. Critically important, there's going to be no solid-state mass transfer limitations in these types of devices. And these are real devices. They offer high power, and hand in hand with that comes high reliability. Often when we have very high kinetics, the life cycle improves tremendously. And these devices are often very complementary to batteries. They can help take over in situations where the currents become very, very high. And in some cases, they even take advantage of battery-type electrodes for hybrid devices that then bridge the gap from electrochemical capacitors to batteries. And the third thing I want to talk about is emerging materials and concepts in the field where new materials are coming online and they are coupled with new characterization techniques that are causing us to really rethink what is happening at electrochemical interfaces. And following in the footsteps of what Stan talked about with intercalation reactions, I think these types of mechanisms will become critical for obtaining simultaneous high energy and high power. At the end, I'll talk about how at these types of materials, often we're talking about nanoscale electrodes, confinement effects become crucial to understand and are a really exciting area for fundamental research. So first, what are electrochemical capacitors? They also go by the names of ultracapacitors and supercapacitors, but I like to keep the adjectives out of the name and just call them electrochemical capacitors. And they reside on this Ragone plot kind of spanning the length scales between dielectric capacitors and batteries. And another way of thinking about this is this distinction between surface storage and bulk storage. Since this plot was made, there have been tremendous advances in electrochemical capacitors, and that's what these red and blue stars indicate on the curve. So this is not an endorsement of any type of product, but this is a recent available electric double-layer capacitor on the market, offering capacitance of 3,200 farads, specific energy of 6.82 watt-hour per kilogram, so definitely modest in comparison to batteries, but a whopping power of 32 kilowatts per kilogram, and a million cycles for charge-discharge, which is really tremendous. These devices can be hybridized, and that's what that blue star indicates, and this is an example of a commercially available hybrid lithium-ion capacitor, where the specific power in the final package device is 13 watt-hours per kilogram. It does take a nosedive when it comes to specific power slightly. Now we're talking about 11 kilowatts per kilogram, but still 600,000 cycles. And you can see also from this Ragone plot that the charge-discharge timescales that are offered by these devices are on the order of seconds, which is several times faster than what we would think of charging and discharging something like a battery, where we're talking about, hours or maybe tens of minutes at the very, very fastest timescales. So electrochemical capacitors offer these high power densities. They can deliver and accept large currents quickly, excellent kinetics, very high energy efficiency at high power, and I want to emphasize this energy efficiency. The fact that you have high electrochemical reversibility means that you should have much less heat generation at very high rates, and this is critical. The intermediate energy densities mean that unlike dielectric capacitors, you can think of using these devices to store some smaller portable electronics, and the reliability means that these are things that you might want to use for applications where you don't want to have to exchange out your energy storage device very frequently. So this is an example of many of the different applications that are utilized for electrochemical capacitors, but it is worth to note that the market size is much smaller than for lithium-ion batteries. It's estimated at about $1 billion currently, but is expected to grow with future advancements. And these are examples of manufacturers, domestic companies like Maxwell Technologies, but also many international companies, most of whom actually specialize in the manufacturing of dielectric capacitors. So it's also kind of a bridge to the electronics industry, if you will. So where the field started was in the 1950s, actually an industrial research lab outgrowth from General Electric, the first patent granted to electric double-layer capacitors, where they were considered at the time to be a type of electrolytic capacitor. And the mechanism by which electric double-layer capacitors store charges is actually very deceptively simple, involving simply the electrosorption of ions at a high surface area electrode. So the diagram for this paper comes from Tito's very nice work in Physics Today, where we see that during the charging process, you have the formation of double layers at each of the electrodes, the positive and negative electrodes, and during the discharge processes, these ions simply desorb from the surfaces and then can be used to power some devices. There's no Faradaic charge transfer reactions that take place, and there's no solid-state mass transfer, which is why the commercial devices can reach those extremely high power capabilities. So what happens at the electrochemical interface is we're storing charge at the electric double layer. And the reason the capacitances of these devices can be so much larger than a dielectric capacitor is that now the separation distance between our positive and negative charges are essentially what is formed at that electrochemical interface. So each electrode interface is a separate capacitor. And that distance between the positive and negative charges is just a few angstroms. And that's the critical thing that electrochemical interfaces afford. The double-layer capacitances range in magnitude from about 5 to 20 microfarads per square centimeter, giving rise to specific capacitances of about 100 farads per gram or so. And so this is the mechanism by which this works. And the materials of choice have always been carbons, different types of carbons, which offer very high conductivity and large surface areas, good corrosion resistance, and so forth. And these materials behave electrochemically exactly how, almost exactly as an ideal capacitor would behave. And this is a cyclic voltammogram of activated carbon at 20 millivolts per second. And you can see that it offers a constant capacitance over nearly the entire potential range. So we can compare more fundamentally the energy storage differences between batteries and double-layer capacitors. Ideally, batteries would provide a constant potential with the extent of charge as illustrated on this curve here. And as a result, when we calculate their energy densities, it's just summarized as the energy is equal to the charge Q times V, essentially the area of this rectangle. For a capacitor, a double-layer capacitor, ideally you have this linear potential versus degree of charge-discharge plot. And if we assume that we could match the capacity of an electrode, a battery electrode, which would be very difficult to, but let's assume we can do that, it shows that even then, at most, the energy stored by this type of a device would be half of what you could get with a battery. And that's because of this continuous linear potential dependence on the state of charge, which makes this area of a triangle, which we summarize as E is equal to 1/2 CV squared. The inverse slope of this line becomes the capacitance. And that's really what kind of fundamentally drives the differences between the energy of these materials, of these devices, rather. Something else to notice from this curve is that because batteries undergo physical and chemical changes, there is a hysteresis between their discharge and charge that grows larger and larger as we go to higher currents. In the case of double-layer capacitors, these mechanisms are not present, so you can get nearly ideal reversibility, and that's why these arrows are drawn on the same line. And so when you go to very high power densities, that energy efficiency is very, very high. And that results in also very high reliability, excellent cyclability with the 100,000s or million of cycles that are afforded. Here's another comparison showing that at timescales of about 10 minutes or slower, lithium-ion batteries can do a pretty good job of maintaining their energy density. But as you push them to faster and faster timescales, not only does that energy density decrease, but you have the separation between the charge and discharge, the hysteresis or the energy inefficiency gets larger, versus the double-layer capacitor, which has the more modest energy density, maintains it almost ideally, and at some point there's a crossover between the two. So what this chart also shows is there's actually a large landscape within which to play to find devices that can operate in this region and still maintain very high energy efficiency. And so that's one of the motivations for generating hybrid devices, where we now take double-layer capacitors and we pair them with intercalation-type electrode materials. And I'll talk a little bit more about intercalation materials in a second, because they are a very special type of battery storage. And so when we do that, when we combine them, activated carbon electrode, for example, with graphite or a lithium titanate anode, we have the continuously varying potential of the activated carbon, paired that with the nearly constant potential of something like lithium intercalation and graphite, and now you have hybrid devices that can offer around 70 watt-hours per kilogram. That's on the basis of the electrode materials. So in the packaged device, it would be a little lower. Nevertheless, these types of hybrids still suffer the power limitations of the battery-type electrode. So the field of electrochemical capacitors has always been focused on ways to increase the energy without decreasing power. So when we look at what goes into the energy of any type of a energy storage device, we know that it's dependent upon the voltage as well as the capacity. So we can think about increasing the energy by two mechanisms. One is to increase the capacitance / the capacity of the electrode. The ways that we could do that is going to high surface area carbons, but they're already using carbons that are well over 1,000 meters squared per gram. So that seems to have reached some limitation. The other is to look for materials that are called pseudocapacitive that involve now surface charge transfer reactions or intercalation reactions. And then the other mechanism, besides modifying the electrodes, is to think about using wider potential window electrolytes, where you can increase the voltage range of the device. I'm going to spend some time talking about the capacitance / capacity aspect. That's where most of my research has focused and represents a large degree of the work in the electrochemical capacitor field. And I think it's worthwhile to take or revisit a little bit the concept of pseudocapacitance, the time in which it emerged, in which it developed, and then how it came to encompass and be manifested in the field of electrochemical capacitors. So pseudocapacitance is a term that's used to encompass reversible Faradaic surface reactions, chemisorption nominally, that could be useful for increasing the areal and thus the gravimetric capacitance of these types of devices. Importantly, such processes are again not limited by solid-state mass transfer, meaning that we don't have phase transformations taking place, we don't have solid-state diffusion limitations. And where this developed was in the early 1960s by considering electrochemical adsorption processes at surfaces as Langmuir or Frumkin isotherms, formalisms developed by Conway, as well as others. And so the idea is that if you have something like a gold electrode and you have the adsorption of hydrogen on the surface, this process right here, nominally your cyclic voltammogram begins to look like this. And you have what's typically assumed to be the double layer contribution here highlighted in white, but then you also have these Faradaic peaks that are incredibly symmetric, giving rise to a mirror image cyclic voltammogram. And those are associated with this chemisorption process. So what Conway did is he assigned this, he thought of this as an extension of Langmuir adsorption that could have to it assigned a pseudocapacitance, CP, that is dependent on this adsorption coverage as an extension of the state of the potential. Essentially a capacitance, but that one that was linked to a Faradaic mechanism. And importantly, such processes trend kinetically the same exact way as a double layer process would be. For example, your peak currents would vary linearly with the sweep rate. So it wasn't really until about a decade later that this concept was considered useful potentially for energy storage, and that was with the discovery of very, very capacitive response of thin film ruthenium oxide. And it looks something like this. So this is hydrous ruthenium oxide, cyclic voltammogram at 2 millivolts per second, a specific capacitance of 720 farads per gram. So several times larger than what you can achieve with activated carbons. Based on the BET measured or surface area, that would correspond to an areal capacitance of about 1,000 microfarads per square centimeter. So tremendously bigger than what has been measured at activated carbons. In situ X-ray absorption work has shown that this process is linked to changes in the ruthenium oxidation state that are nearly linear with the extent of charge. Although, of course, ruthenium oxide being a metallic conductor, we don't really think about the charges localized just on the ruthenium cation itself. And then this really seminal work by Deborah Rollison on using pair distribution function analysis showed that the structure of this is very, very unique. You have these ruthenium oxide nanoclusters that are electronically conductive, connected to each other, and separated by hydrous grain boundaries that were providing exceptionally fast proton transport. And this was really the first time that the idea of pseudocapacitance was extended from that adsorption-desorption understanding in the 1960s to something that could now be utilized for energy storage devices. And then something else was happening around this time. We know that a gentleman by the name of Stan Whittingham was working at ExxonMobil on intercalation reactions. And I think it's important to highlight that intercalation reactions are unlike any other type of a battery technology, especially up until that time. Until that time, we thought of batteries as ones where you had a very constant, fixed free energy difference between your anode and cathode. Those were devices that utilized conversion reactions, lead-acid batteries being a kind of a typical example. And so as this intercalation concept took hold, the pseudocapacitance community or folks that thought about adsorption and desorption at surfaces saw similarities between that process as being essentially an ion sorption into a bulk host, and that you could assign an intercalation capacitance or what would be analogous to a pseudocapacitance using exactly the same type of Langmuir or Frumkin intercalation isotherms, for example. However, oftentimes we don't think about these kinetics as being capacitive, that is, being limited by surfaces, because solid-state diffusion dominates in most of these materials, or phase transformations take hold. And this is an example of lithium intercalation into lithium cobalt oxide at a very slow scan rate. We don't see that mirror image response here. But something interesting happens when you start to nanostructure materials. And this is work that is very beautifully illustrating that. When you begin to nanostructure materials, capacitive features begin to emerge. And so something like lithium cobalt oxide that shows a galvanostatic discharge curve that looks something like this, as you make it smaller and smaller in dimensions, begins to look more and more like you have a very strong dependence of the potential on the extent of the state of charge. So you could essentially call that a capacitive, but we know it's linked to cobalt redox, pseudocapacitive, if you will, mechanism. And what's important about this is that now you have materials that are storing ions not just at the surfaces, but actually near the surface or somewhat in the bulk, and providing very, very high current densities as a result. And so I think this concept of thinking about pseudocapacitance in terms of adsorption, desorption processes is important for helping us understand how to achieve simultaneous high power and high energy density, to recognize that intercalation is a unique mechanism amongst batteries, especially exactly because it retains for the most part, the structure material, and that this is the pathway for how we could utilize nominally bulk energy storage with surface-like kinetics, which is how we want to push forward on that Ragone plot that I showed in the beginning. So recognizing that structural stability is key, we found that indeed if you have a conductive host, like niobium oxide when it becomes lithiated, that undergoes a pure solid solution intercalation mechanism, which is what we measured with in situ X-ray diffraction, you get cyclic voltammograms of this material now that actually begin to look like mirror images with these redox peaks being superimposed right on top of each other. That large cathodic peak that you see at the lower potentials here is due to the electrolyte decomposition, an irreversible process. And again, thinking about even the potential of intercalation reactions as being limited by surface processes is very important in pushing ultimately the power capability of these materials. And this focus on looking fundamentally at what types of mechanisms give rise to simultaneous high energy and high power is something that we've been investigating in my group now at NC State, where we've been comparing proton intercalation into a hydrated tungsten oxide and comparing it to anhydrous tungsten oxide, which is known in its own right to be a fairly high proton conducting material. And what we see is that when we go to very, very high rates, we're talking about a half a second charge-discharge time scale for hydrated tungsten oxide, we see fairly high electrochemical reversibility for proton intercalation when water is in the structure. The anhydrous material, we still see the Faradaic peaks are present, but their hysteresis is much, much greater. And what's interesting is that initially we thought we would see something like proton moving through these hydrated layers, but operando experiments told us to maybe consider the structural stability of the water-containing materials, and that's because we saw much smaller deformations as a function of the applied potential when water was in the structure compared to the material where water was absent. Also, we saw no scan rate dependence and very little hysteresis. Again, with operando characterization, we found that the hydrated materials were able to undergo very, very reversible structural transitions at timescales of 70 seconds as well as 7 seconds. And these are some of the fastest operando X-ray diffraction experiments for energy storage devices, I believe, that are out there. And we find that what's likely happening in these materials is that the water is limiting the structural degrees of freedom that can be possible as protons intercalate, and that this essentially stabilizes the structure, fixes it, and makes it respond incredibly quickly. So as we go to these types of mechanisms where we're now saying we have processes that occur on 7-second timescales that are Faradaic, there has been intense interest in the community to discriminate between capacitive mechanisms. And what I think it drives to is to understand the fundamental nature of non-Faradaic versus Faradaic processes. And I'd like to illustrate that with these two examples. The picture that I showed you at the beginning of charge storage at the electric double layer is actually totally inapplicable to what happens in an electric double layer capacitor. The situation looks something like this. When you have these activated carbon materials, they have very, very tiny pores. That's how you get high surface areas. Within these pores, the electric double layer looks quite different than it does at a planar interface. And it's illustrated in this schematic as something that begins to look, at least in my eyes, as something that looks like intercalation. In some cases, you even have the desolvation of these cations taking place. Compare that to what we typically consider as Faradaic in the pseudocapacitive community, which is the responsive Bernesite MnO2. Nominally, this picture looks very similar to the one on the left. And so this is examples of some of the discussions that are taking place in the scientific literature, and I think it's a very exciting area to understand. What I think it comes down to fundamentally, in my opinion, is that we're in these types of materials where we're increasing surface areas, we're really blurring the line between what is an electrode and what is an electrolyte. We're making, we're asking the question of where to draw the electrochemical interface, and so these are examples of ionic liquids that are confined between layers of carbons, forming what are called non-Coulombic interactions, meaning that they're actually pairing up with ions of same charge, something that would typically be very, very energetically unfavorable in the bulk. And that when you simulate the induced charges on the carbon walls, you see that it's not homogeneous. There's actually regions where charge appears to be highly localized. So everything changes when you're looking at mechanisms under confinement. And from the Faradaic side, you have materials such as MXenes, which are derived from selective ion etching of transition metal carbides that contain layers of what could be called an electrolyte that potentially could be enabling very fast proton transport and access to surfaces throughout their entire volume, giving rise to cyclic voltammograms that look like this with very reversible Faradaic peaks, but now we're talking about cyclic voltammograms being run at 10,000 millivolts per second, something that before, I think, the past few years, nobody would have thought would be possible with any type of Faradaic mechanism. And so I'd like to conclude here on my key points, the fact that, yes, we can store energy at electrochemical interfaces. It gives rise to tremendously high powers. There's commercial devices available that are complementary to batteries, that take advantage of batteries and hybrid devices, and that now when we start to have new materials coupled with operando methods, I didn't spend a lot of time talking about theory, but that's integrally coupled to this, we're coming up with very new understanding of what the electrochemical interface looks like, which I think are applicable not just to these types of energy storage devices, but really all electrochemical interfaces. And with that, I'd like to thank my research team, the graduate students and postdocs that participate in this research, my collaborators, many of whom we work together also in an EFRC. This is the Fluid Interface Reaction Structures and Transport EFRC, and the support of the National Science Foundation for our tungsten oxide hydrate work. And thank you all very much for your time.
Any questions? Are you kidding me? Come on. Yeah.
I'm Laura Gagliardi from the University of Minnesota. So it's a question to this talk, but basically also back to the comment of the previous person. So theory has been mentioned several times this morning. I'd like to understand what is the role of theory in all these efforts, because I see two ways of including theory. For a lot of experimentalists, theory is like checking a box saying, oh, the theoretical prediction confirms our experimental measurement, and it's like a little decoration. For other people, theory really adds something important that really advances the fundamental understanding that, for me, it's very important because, honestly, we cannot make progress in our society if we don't advance our fundamental understanding. And I'd like to know how things are done in your center, in the previous centers.
So I don't have specific examples of the center theory and experimental work in my presentation. I was trying to capture different things from around the world in the field. But I would say that they are integrally coupled together, particularly because our characterization tools often need theory to be very tightly complemented to those efforts. And let me give you an example. This is not from our EFRC, but this paper here, where what's shown on the bottom here is from simulation. This is not an experimental result. This is we could not capture this experimentally, that the induced charges on the carbon were such, because that's the way that they used to explain the ability to form these non-Coulombic interactions that's observed experimentally from X-ray absorption measurements. And in our work now on various redox active materials, the theory is very integral to understanding the structure-property relationships, but also what happens when what the structure of that double layer, if you will, would be in a situation like this. We cannot capture the details of that experimentally yet.
I mean, it's also the case that, theory has come a long, long ways, from the early days of an infinite slab of a perfect crystal at 0 Kelvin. Now people are introducing, interfaces and electrolytes and fields and defects. And I think that's having an enormous effect, in our understanding of these things. So I think we need more theory, not less.
Hi, Veronica from PNNL. Yes, I would like to
Speak to the microphone.
Yes, I would like to emphasize this interaction between theory and experiment. At PNNL, we have the Chemical Transformation Initiative, which is actually about this type of science and how we interact directly with the experiment to answer Laura's question. And it's not just to tick the box, it is to make specific recommendations to the experimentalists, also help understand why they get the results and how they can modify their material to, in fact, obtain better results. And, of course, addressing the issues of the double layer is a huge point.
Yeah, and I think it's ubiquitous in all the electrochemical systems that we're going to talk about. So I think it has tremendous implications.
Since we're running a little bit... Okay, dude, one last time.
Thanks. Quick question. Jake Yeston at Science. I'm wondering, you put up specs on the first slide that looked quite spectacular, and so I'm wondering what are the big challenges still remaining in this field? Is it getting the cost down? Is it getting the cycling even higher than a million, or where's it going?
Right. So it's from my perspective as an academic researcher, it would be all of the above, but particularly the energy density. I think it's a fundamental, I think Esther has a paper called Holy Grail in energy storage to have simultaneous high power and high energy density. How to decouple those, we're always separated. How do we have them move together? That's a fundamental question.
I think the design criteria are infinite energy, infinite power, last forever, and cost nothing, right?
That's right.
With that, let's close the morning session.